Okay, hi everyone, welcome back to lecture one. So now we're going to finally discuss some algorithms, and today we're going to talk about amortized analysis. Okay, so the overview of the class will be, well, why should we study amortized analysis and what is amortized analysis? And we're going to see three different types of amortized analysis, and then we're going to work through one example using three different kinds of amortized analysis, okay, which is the aggregate analysis method, the accounting method, and the potential method, okay? All right, so why study amortized analysis, right? So in your first data structures course, right, like you learn how to devise data structures that had good worst case or average case behavior per query, right? So each query, you had a guarantee on the running time, right? That was your goal back then. So if you think about it, let's just do a simple review here of what you learned, right? So, all right. So if we had a doubly linked list, what was the search time in a doubly linked list? Well, if you have a list of size n, your search time was going to be O of n. The time to insert an element in your doubly linked list was O of 1 time. And the deletion time in your doubly linked list was O of n, because you had to search the element that you want to delete to then delete that element, right? So, and if you have an ordered array, right, what is your search time? Your search time was O of log n search time, right? Because you can do binary search. But insertion and deletion in an ordered array would be like O of n time, right? So, all right. So, and then if we have hash tables, what was the difference between hash tables, right? So hash tables, now here we have a footnote because hash tables is usually an average case analysis, right? Because you have to choose your hash table wisely. And here on average, your search time was constant. Your insertion and deletion time was also constant, right? Because you didn't have a lot of collisions. And balanced binary search trees, right? So here, it was also kind of an average case situation, right? Because usually the worst case complexity of balanced binary search tree is O of height of the tree, right? Which can be theta of n, but on average, you would get like your search time would be O of log n, insertion is O of log n, and deletion is O of log n, right? So, and then we have all these different ways of rebalancing the tree, right? So that we can get those average case to be O of log n, right? All right. So, and now, why should we study amortized analysis? Well, in amortized analysis, right? So if you notice, like, let me go back to this slide, is that like when we studied these data structures, we had this one mindset, which was like, oh, like each query like is important, is very important, and we want to minimize like the worst case per query, right? But the thing is, this is great, right? Because on one hand, this is great because usually, for example, if you're in the internet, you have this client server model, right? And in the client server model, of course, what you want is you want to minimize the worst experience of your client, right? So you want to make like most queries be like well-behaved, right? So in a sense, you would like something close, very close to worst case, right? Or if not on average case, you want to say like with high probability, all my queries are going to be extremely fast. Maybe one of them will pay something, right? But you want to get this bound per query. However, in amortized analysis, the goal may be different. Like we may be in a different setup than the client server model, right? And we're going to see so for example, one way in which we're different than the client server model while using data structures is if you're running an algorithm, right? So for example, if you're doing the minimum spanning tree algorithm, like the greedy minimum spanning tree algorithm, right? If you go through that algorithm, you notice that many algorithms, you need a data structure to help you do certain operations, right? So for example, in the minimum spanning tree algorithm, what do? Well, you do the contraction algorithm, but then you have to see if things are connected. You're picking your edges accordingly in a greedy way, right? But you need to know if, like, whenever a new edge comes, you need to know if the endpoints of that edge, they are connected to the tree because you don't want to add a cycle, right? Now, in that algorithm, well, what do you need to know? You need to know if 2 points are connected. And how do you do that? Well, to do that, you use a data structure called union find, okay? So this union find, you won't learn in this iteration of the lecture. If you would like to learn about union find, I can give you a video that I recorded from the previous years. But union find is a great data structure because it allows you to speed up the minimum spanning tree algorithm. So here you see an example of a data structure that is actually used to solve an algorithm and not for answering queries in a client server model. So what is the difference between this new setting? In this new setting, our algorithm doesn't care if your worst query took linear time, so long as most of your queries are constant time. Does that make sense? So what the algorithm cares, remember, when you're doing analysis of an algorithm, what does your algorithm care? Your algorithm cares that the total running time of your algorithm is small, right? So it could be the one query takes linear time, but if all the rest of the queries are constant, that's a much better data structure than one that always works with log n time, right? But every time that I query my data structure, I have to spend that log n time. Does that make sense? Because if I make n queries, right, the first data structure is going to give me 2n total running time, whereas the second data structure will give me n log n time, right? And that's a difference that you may not want to pay. Does that make sense so far? So these are just examples, right, where the different settings have different requirements. So, and for that, okay, we need to use amortized analysis. So what is amortized analysis? Well, in amortized analysis, we average the total time required to perform a sequence of data structure operations over all the operations performed, right? So we're interested on that time, okay? So what is the upshot of the amortized analysis is that the worst case cost per query may be high for one particular query or for a couple of particular queries, okay? So long as the overall average cost per query is small in the end, right? Which is what we discussed. Would you prefer to have one query that took O of n time and all the other queries that take O of 1, or would you prefer a data structure that takes always O of log n time, right? Sometimes you prefer the second, sometimes you prefer the first, right? But in amortized analysis, you would prefer the first because the total time required to perform all the sequence of operations would be O of 1, right? The average time per query, okay? But now, one thing to remark here is that amortized analysis is a worst case analysis, okay? What do I mean by that? It measures the average performance of each operation in the worst case. But all we're doing is we're putting all of the operations together and dividing by the number of operations, okay? So let's get to some examples to see this idea. So far, so good? Okay, so we're going to work through some examples, but before we do so, let me talk about the 3 common types of amortized analysis. So the first one is the one that you can imagine, which is the simplest one, right? Which is the aggregate analysis. And what is that? Well, we simply determine an upper bound T of n on the total cost of a sequence of n operations. And this is on the worst case, right? So we just say, okay, worst case, we have this upper bound T of n on the total cost of a sequence of n operations. And the amortized complexity is Tn over n, right? Is the total cost of all the operations divided by the number of operations. That's the most simple one, right? But sometimes this upper bound T of n may not be easy to obtain. So what do? Well, so what we do is we do an accounting method. So what is the accounting method does is essentially it assigns a certain charge to each operation, independent, well, somewhat independent of the actual cost of the operation, okay? So, and then, you know, what the accounting method does is saying like, you know what, like there may be many operations in the beginning that are very cheap to compute. And then there may be one operation in the middle that's really laborsome to compute. But the idea is that if I charge the easy operations in the beginning a little bit more than their cost, maybe this charge that I charge the earlier operations will pay off the expensive operation. Does that make sense? So it's as if every operation is building your credit in a bank. And then once the really hard operation comes, we pay back with the credit that we have. Does that make sense? So we're going to use examples to analyze all of these, okay? But this is the accounting method. Questions so far? Okay. So, and the third method, okay, is the potential method, okay, which comes, the inspiration is a little bit from physics, right? That we assign a potential energy to our data structure, okay? So you're going to come up with a potential energy to your data structure, and which maps the entire state of your data structure to a real number, okay, which is its potential. And this differs from the accounting method because instead of like the accounting method, we're charging each operation, but the potential method is kind of like your data structure has a huge potential, right? So for example, one example of things that are used is like if you have a binary search tree, then the potential energy could be something related to the height. Then when you say, oh, if my tree is very unbalanced, then there's going to be a huge potential, right? If my tree is balanced, then my potential is really small, or vice versa. Okay, so you could think about it that way. So the potential energy tells you something about this data structure, right? And somehow this potential energy, so every time that we perform an operation, we're going to change the data structure. So there's going to be a change in potential. And the idea of the potential method is that it is easier to like account for the real cost of your operation plus the change in potential than just the real cost of the operation. Okay, so we're going to see an example of that, and then maybe that will clarify what I'm saying here. Okay, so this is just kind of a synopsis, right, which will be clearer later. So you can come back to this slide later. So let's work through a simple example. Okay, so a very simple problem, but let's give several analysis to it. Okay, so the first thing is, suppose here's the problem. We have a binary counter C. Okay, so C is a bunch of bits, right? So is initial, C is initially set to 0, and now the output is, what do we need to do? We need to increment this counter up to n. So it's 0, and every time we're going to add 1 to the counter, like 1, 2, 3 up to n. Okay, which is a given integer. Okay, so all right, now here's the question: how many bit operations will it take to increment C from 0 to n? Right? So if you think about it, well, notice here that the worst case time per operation is log n, right? Can anyone see why the worst case time per operation is log n?
Oh, yeah. Because if you think about a bunch of bits, the number of bit flips, and we can assume that we're doing a bit flip in constant time or whatever. The number of bit flips is equal to the position of the last 0 plus 1. And if you think about n, well, n has, let's say k bits, and definitely you're not going to need to flip more than k bits, because that would mean you have a number bigger than n.
Correct. Yeah, exactly. So if I may just express with a pen, which I have the advantage of having a pen here and being able to write, exactly. So suppose that we have the number, like, suppose that n, or let's say, like, suppose that we are suppose that n here is bigger than 2 to the k, right? But let's say it's less than 2 to the k plus 1, right? We're in kind of this situation. And then we're incrementing a counter, and let's say that we're at the step. So we know that k here is really log n, right? Like is roughly log n. So then now if I have the number 2 to the k minus 1, right? How do I express, 2 to the k minus 1 is on the bottom. 2 to the k minus 1, how do I express this number in bit complexity, right? So the bit complexity of this number is exactly 1, 1, 1. Well, it's going to be 0, 1, up to 1, right? Now, if I increment this guy and I go to 2 to the k, right? What Eli said is that, well, how many carries will I have, right? Because if I had just like, let's say, if I'm incrementing 2 to 3, I have no carry. So the cost of this is 1. right? Because this is 10, this is going to be 11. I just flipped one bit. But now if I flip any of these bits, I'm going to have, if I flip the first bit, I'm going to carry over, right? And these carries are going to go all the way to the end. So this operation here, 2 to the k, will be 1, 0, 0, 0, 0. So how many bit flips do I have here? I have k bit flips, right? So the cost of the operation is k, which is log n, right? So if we remember, if we were to bound this by bounding the worst case time per query, and then just saying, oh, we're doing n increments, so the upper bound is O of n log n, right? So that's a crude upper bound. That's a correct upper bound, but it's a crude one. We can do better, right? Because most times, like for example, from 2 to 3, I'm only going to do 1 bit flip, right? Or even like 1, 0, 0, 0, 0 to like 1, 0, 0, 0, 1, I'm only going to do 1 bit flip. So oftentimes I'm doing only 1 bit flip, right? This situation where the k bit flips happen is really rare, right? So, okay. So, but, you know, the thing is, what is the catch? Well, overall, we see that the most significant bits, right, they get updated very infrequently, right? So the question is the above analysis tight? And what we're going to see today is that the answer is no, it's not tight, right? Because now let's just explore this concept here that like, well, the most significant bits get updated very infrequently, right? So, all right, so let's see why, right? So, all right, here's the question. How many times will we flip the kth bit? Okay, so suppose that, you know, our number here is, well, let's say that s is equal to log n, right? So, you know, let's say like, okay, we want it to be an integer. So we have all these many bits here, right? So we have, and let's say that, you know, let's say that s is 5 for now. Okay, so, all right. So how many times will we flip, let's say, this bit here, the third bit? Okay, so this is the most significant, right? So this is bit 0, this is bit 1, this is bit 2, 3, 4. How many times will we flip bit 2? Right? So, you know, if you do the calculation, I'm just going to go through it, but you can do it like at home just because we're running out of time today, is that if you notice that the amount of times that we're going to flip the kth bit, okay, so let me move this a little bit over, right? Maybe let me delete this. So if s is equal to log n, and then the kth bit, well, when I flip the kth bit, what am I doing, right? To flip the kth bit, I need to increase. So if I flip that bit, if it was 1 to 0, it means that I have a carryover. And if it was 0 to 1, right, it means that I walked. So let's see. When I flip the kth bit for the first time, it has to have been like, so if this is the kth bit, well, it has to be when I have all ones, right? So these are the previous bits. And this is the kth bit. So once I flipped, so to flip the kth bit, I have to do how many increments? So we need like 2 to the k increments to change the kth bit, correct? Because the first time that I change the kth bit, I have this situation. The kth bit is 0, everybody else has to be 1, which means that I had to have done 2 to the k minus 1 increments before, right? And then the 2 to the kth increment, I'm going to flip the kth bit. Does that make sense? So then, like, how many times do we flip the kth bit? So if to flip the bit, the kth bit, we need 2 to the k increments, right? We flip the kth bit, well, n over 2 to the k times. So the upshot here is that this happens very infrequently. Right? So now let's see how many times did we flip each bit, right? So if we put it all together, right? So how many times, what is the number of bit flips? So we can just write here like the number of bit flips. But what is the number, the total number of bit flips is equal to the sum And this is the what? Number of times we flipped the kth bit, right? In our n increments, right? So if I sum the number of times that I flipped each bit, I get this sum, correct? And now this sum, note that this is smaller than if I just drop the upper index, like the log n index, and I just sum n over 2 to the k, but this is the geometric series, so this is equal to 2n, right? So now note that, just by doing this amortized analysis, we actually see that the running time of this binary counter problem is actually 2n, at most 2n, right? As opposed to n log n. So you can see the advantages here in the simple example, right? Does that make sense? Any questions so far? All right, so then let's get going. So now let's go through the accounting method, right? So now suppose that the actual cost of each operation of an algorithm is C, is CI, right? So this is the ith operation, right? So this is the cost of the ith operation. Now, this may be hard to track, right? Like in this problem that we have is not so hard to track, but in general, it could be hard to track, right? So in the accounting method, what we do is at each step of the algorithm, we actually assign a charge, and the charge is gamma I, which may be different from CI. And the upshot of the charges is that they have to respect the following inequality. They have to respect this inequality, that for any number of steps, okay, the sum of all the charges up to the L step has to be bigger than or equal than the sum of the costs of each step, okay? So, of course, the first charge has to be bigger than the first cost, but the first charge plus the second charge has to be bigger than the first cost plus the second one. So it could be that the cost of the second operation is more expensive than the second charge, right? But we charged more already in the first operation. Does that make sense? So that's the upshot of this inequality, right? Is that always the sum of the charges is bigger than the sum of the costs, but individually, a cost can be bigger than a particular charge, okay? So now the total charge up to step L is always greater or equal than the actual cost of operations, right? So, okay. So in other words, what we're saying is we are charging certain operations before they happen, right? So let's see how this happens. So, okay, by the way, and just another remark is that if we manage to do the above, then we know that the total cost, which is this part, right? Like the total cost is less than or equal than the total charge, right? So if it's easy to take care of the charges, much easier to handle the charges than the actual cost, and we have this inequality, great, right? We can use the charges to give an upper bound, okay, of our algorithm. So let's see how to do that for our problem. So here's our problem. So we have a binary counter C, and this is initially set to 0, and we're going to output, we're going to increment this counter up to n, right? And here's the thing, is there a way to charge earlier operations for the cost of subsequent operations, right? And that's the upshot of the accounting method. And what do we do? Well, so suppose that we actually charge the cost of clearing a bit. And what does it mean? What do I mean by clearing a bit? Is to change the bit from 1 to 0, right? So what we're going to do is we're going to charge the cost of clearing the bit, of changing from 1 to 0, to the operation that actually sets the bit to 1 in the first place. Does that make sense? So for instance, let me just run a quick example here. Suppose that I start with like 0, 0. And then as I go from 0, 0, I increment to 0, 1. And so this cost me 1 because I flip only 1 bit. But let me charge 2 to this operation because I'm charging it also the cost of clearing the first bit, which is sending 1 to 0. So in the next step, I'm going to have 1, 0. Now, how many bits did I flip here? I flipped 2, right? But one of these operations, right, the operation of clearing this bit is charged here. Does that make sense? So I'm charging the operation of flipping the first bit from 1 to 0. I'm actually charging in this 2 here, right? So the 2 charge is 1 to the cost of flipping the bit from 0 to 1 plus the cost of clearing it later. Okay? Does that make sense? Okay. So now note that if we flip k bits during an increment, note that we already have charged k minus 1 of those bit flips to earlier bit flips. And why is that? It's because, right, if we flip k bits, what is the only situation in which I can flip k bits? Is if I have, well, the k plus 1 bit is 0 and the other bits are 1, 2, all of them are 1, right? So these are k bits. Right, sorry, these are k, sorry, I flipped k bits, right? So these are the k minus 1 that I'm carrying, and this is the last bit that I flipped. Now, if I flip k bits during an increment, I already charged k minus 1. And why are those? Like these guys here, I have already charged. They're clearing. Earlier. Does that make sense? So I have charged this clearing to when I set the bit to 1 last. Right? So it's just in the same example that we saw, right? Like the 0, 0, 0, 1, 1, 0, right? Like I charged that 1 to 0 flip before. Okay. So, all right. Now note that if we flip the k bits, right, we're going to set this k minus 1 bits to 0, right? So that we have the carryover. And that's why, like, we have already charged those because we're clearing them. So, okay. So instead of paying for k bit flips in that increment, right? Like when we go from like 0, 1, 1, 1, 1, 1 to 1, 0, 0, 0, 0, 0. Instead of in this operation paying for k bit flips, we will charge this operation that costs a lot more. We're only going to charge this operation 2, a cost of 2. And what is the cost of 2 that we're charging? Well, we're charging the cost of setting the bit to 1, right? So we're going to charge the cost of setting the 0 to 1. This is the first cost. And the second cost, the second charge is the charge to clear the bit. And this charge will happen in the future. Does that make sense? So we know we're building credit, right? Because we're assigning the extra cost to later, right? So in particular, we know, again, we have proven here that the total cost is less than or equal than the total charged. But what was the total charged? Well, at each time, what did we do? We're charging 1 for the cost of changing that bit, and we're charging another one to clear the bit. So every time we're charging 2, right? So this is the charge per operation. And n is the number of operations. Does that make sense? So it's very easy to handle the total charge here, right? And all we needed to know is that this upper bound, the total cost. Does that make sense? And this is the analysis that we did in the previous bullets. So you can see this playing in action, right? Does that make sense?
Excuse me, Professor. I have a question.
Of course.
So I understand the 2 methods with the example, the differences. I understand that, but why these 2 methods? Why the second method is important? Ultimately, we're finding this kind of the same thing, right? I mean, my question is the bit that is changing, like that in the algorithm section, that is not getting faster anymore. Like we had to change the bit, we had to spend the time there, right?
Right, correct. Yes. So that's a great question, right? And usually, so in this example, it just turns out that both analyses go through, right? But in practice, and when I say in practice, I mean in theory, right? Like whenever you're analyzing algorithm, it may be hard for us to actually account for the cost, the real cost of each operation. Okay, as you're going to see tomorrow we have a highlight, And a highlight of amortized analysis is the problem of splay trees. Okay, so tomorrow you'll see that it's incredibly hard to keep track of the cost of each operation. Okay, it's impossible. So then, like, it's really impossible to do the first method. Okay, and sometimes it's even difficult to do this accounting method. Okay, so sometimes it's even hard to do this one, and that's why we need the potential method. The potential method is the most powerful method that we have. Okay, but it's also the harder one to apply, as you're going to see tomorrow. It's going to be quite complex. Okay, splay trees are quite complex, but you will see that they're quite complex because it's really hard to keep track of what the splay tree is doing, like at each amount of time. Does that make sense? So that,
Yes.
yeah, so, and that's a great question. That's an excellent question. And you should always try to do the first one, which is the easiest. And then you're going to see that in most problems, that first one won't work. And then you go to the accounting method or potential method, depending on what you need to do. Does that make sense?
Yeah. Thank you so much, Professor.
No problem. No problem. That's an excellent question indeed. Right. So it's hard to see on the easy example, because that's the good thing about the easy example is also the bad thing about the easy example. Right. But tomorrow you'll see, it will be very clear tomorrow that the first method is not possible. Okay. So, okay, just for the sake of time, I mean, I can run through this I was just going to do an example with 3 bits of the accounting method, but it looks like you guys got the gist, and I will save that for office hours. I'll put it. And if you want this example, it will be done in office hours. Yeah. The example of the accounting method. And again, the formal analysis, I just want to put the formula just so that you learn how you can write those things, right? Is that, so once we proved, right? So what is the charge per operation? Like charge to operation I is gamma I equals to 2, right? Which we said 1 for setting the bit, for flipping the bit, which is the cost of the operation, and 1 for the clearing of this bit later. So the charge of operation I is gamma I equals to 2. And we proved in the previous slide, right? So in the previous slide, we proved that this assignment, like this charging, which we call the charging scheme, right? Like charging scheme is valid. Because we proved that if I'm going to clear a bit, I charge for that operation earlier on, right? So we already proved that. So what did we prove in the previous slide? We proved that sum of gamma I is greater or equal than the sum of CI, I equals to 1 up to L, I equals to 1 up to L. We proved that in the previous slide. So now we have this charging scheme. So as we said before, the total cost, like I equals to 1 up to N of CI, is less than or equal than sum of gamma I equals to 1 up to N. But each gamma I in our charging scheme is 2, which means that this is sum 2, I equals to 1 up to N, which is exactly 2N. So we get the same result, right? And now let's just see a little bit of the potential method. And sorry for going over time, but let's just see a little bit of the potential method. And here, yeah, maybe let me just put it here, like, and you can do this as a practice problem, right? Just practice maybe putting like N equals to 5 or N equals to 9, for example, right? Like just run this increment to this and see how the accounting method works for these 2 examples, okay? So that's a little homework. All right, now let's talk about the potential method, which is the third one, which is most powerful, and the one we're going to see tomorrow in our highlight. So suppose that the actual cost of each operation, okay, of an algorithm is CI. And again, you should think of this like you should kind of ignore this point that is not valid for this problem and just think of that CI is hard to track, the cost of the ith operation, right? Because it's like, here we know, but in general, we don't know how much the ith operation will take because the processes will be more complicated, more complex. So then the potential method is the following. We're going to assign a potential phi of I to a data structure at time I, right? So in the amortized cost of the ith operation will be what? Well, the amortized cost of the operation will be gamma I. We're also going to denote by gamma I, but gamma I will be equal to the cost of the operation. So this is the actual cost. Remember, actual cost, right? Plus, now we're going to have this term here that tracks the change of potential, change in potential. Change in potential. Okay, so the total amortized cost is the actual cost of the operation plus the change in potential. Does that make sense? Now, okay, so what is the good part about this? Well, the good part of assigning the potential method to the data structure is that if you sum the amortized cost, right? So this is total amortized cost. Right? This is equal to what? Well, is the sum just by the definition, right? So this, the first equality follows by definition of the term gamma I. But now, if you notice, well, this, the sum of the gamma I minus 1, this sum telescopes. And what I mean by the sum telescopes, well, we're going to have like phi of 1 minus phi of 0, and then we're going to have plus phi of 2 minus phi of 1. So we can see here that like phi of 1 gets canceled, right? And so on. Does that make sense? This is what I mean by the sum telescopes, right? So let's do another one, like phi of 3 minus phi of 2, right? So then you can see the phi of 2 is canceling as well. Does that make sense? So in the end, because the sum telescopes, we just obtain like the final change in potential plus the actual cost. So this is actual cost, change in potential, right? Like change in potential from the beginning. Does that make sense? And now we say that if we had that phi of k minus phi of 0 is greater or equal to 0 for all k, okay? And if we have this, we say that this is a valid potential function, okay? So being valid potential function is exactly having these properties, like that the potential compared to the initial potential is always greater or equal to 0. Okay, so if we have this condition, if we're able to prove this condition, then the total amortized cost will be an upper bound on the total cost, right? Because in the end, if this is valid, it implies that this is greater or equal to 0, right? Which implies that this whole thing here is greater or equal than sum of the CI. Does that make sense? So that's why the potential method is a little bit more complex, but you'll see that it has these advantages, and you'll see tomorrow. Okay, so all right, let's go through this problem and let's use the potential method here, and then we're going to be done, right? So, okay, so we have our increment problem. And okay, is there a way to assign a potential function to the entire data structure? And well, you may even think, what is the data structure that we have at our hands? Well, the data structure that we have is actually the bits that we're incrementing. This is our data structure, right? The data structure is the bits in this case, right? Is the data structure that stores the number that we are at. All right, so how do we assign this potential function? So here is a potential. So the potential will be phi of I is the number of bits with value 1 at step I. Okay, so what is phi of 0? Can anyone tell me what's phi of 0? So phi of 0 is, oh, sorry, there's something in the chat. Exactly, right? So phi of 0 is actually 0 because we start at 0. So all my bits are set to 0, right? And note that, okay, is this potential function valid? The first thing that we have to check is like, okay, I'm coming up with the potential function. Is it valid? Why is it valid? Because we know that phi of k, well, k has at least, right? Like, so if k is different from 0, k has at least, because k has at least 1 bit, 1. Right? The only number that have all the bits 0 is the 0 number. Correct? So we know that the potential is valid. So, and this is always something we need to prove, right? Otherwise, our proof will not go through our proof, right? So, all right. So, all right. And again, yeah, that's what we said, right? So this is a valid potential function. And okay, so what is the amortized cost of the ith operation? So let's look at the amortized cost of the ith operation, right? So what's the cost of operation I? Well, the cost of an operation is, is the number of bits that I flipped that go from 0 to 1, correct? Because I flipped those bits, plus the number of bits that I flipped from 1 to 0, right? This is just saying that this is the total numbers of total number of bits that we flipped. Does that make sense? So you can only flip a bit if you send it from 0 to 1 or from 1 to 0. Okay? Is that clear? Okay. So then we have this. Now, what is the difference in potential function? Remember, the difference in potential will be what? Well, this is the number of 1 bits in the ith after the ith operation, and this is the number of 1 bits that I had before. Right? Now, what is the difference in potential? The difference in potential is something that I can always keep track of, which is, and that's the whole point of the potential function, is that I may not know the potential at the time, but I know kind of the difference in potential. Right? Okay. Thank you for the question. Let me just address this question. So yes, so the slide is so this what we proved this. So the question was that perhaps someone thought in the class that like the sequence of phi i's had to be increasing. Okay, and that's actually not the point. That's actually not what we want, right? Because sometimes what we want is that, if the potential is really high, at some point the potential will drop, and because it's essentially building credit. Does that make sense? Think of the potential as you're building credit for later. So if you keep increasing your potential, right, at some point you may have an expensive operation, but that expensive operation will be paid for with the potential. Okay, so it's something that potential is there to help you regulate. So let me go back to the slide above, and we can review this. Yeah, and this is a great question, because this potential method is the more complex one to understand. The only thing that we need is that phi of k minus phi of 0 is greater or equal to 0. It's always comparing to the initial potential. Does that make sense? Because in the end, what we have is that all we want is that the sum of the amortized cost is an upper bound on the sum of the cost, right? And we use just this, and because the sum telescopes, right, at some point your potential may decrease, so long as it doesn't decrease so much. Does that make sense? So yeah, so the potential will increase or decrease so long as it's always bigger than the initial. Yes, go ahead, Ellie.
It's Eli, first of all.
Okay, sorry, Eli.
So I guess in this sort of little example, we've got sort of this way of analyzing algorithms by averaging out their costs, but with the potential method, for example, and I guess this also applies to the accounting method, I feel like it's a bit of a cheat, because we're kind of like picking the potential in order so that it satisfies the inequalities. But like, in the end, how do we do this? Like, if we don't know the cost, the real cost, how can we pick a potential that's satisfactory and make it work?
Correct. That's a great question. So the idea, okay, so if I just may rephrase Eli's question, is that he's saying, well, it feels like we're cheating because if I just add this difference in potential, I may already know the cost of the operation. So then I'm not really doing anything. I'm just kind of trying to impress you, but not achieving anything, because you could have just, if we know the cost, we can deal with it. But here's the difference, right? So, and I'll get back to the other question in a little bit. So there's another question in the chat. So, okay. So if we notice here, okay, the cost here of operation I, is we're not computing any cost. Do you see, like, what is the, if I ask in the ith operation, so here's the advantage of the potential method, is that here, look, in the ith operation, can you tell me the cost of the ith operation? Like, how much does it cost? 1, 2, 3, 4, 5. How much does it cost?
I think every operation costs, I think we worked out what it costs.
Actually, we didn't. At any point, we did not work out how much it costs, right? Because the only thing that we said that it costs is the number of bits that go from 0 to 1 plus the number of bits that's 1 to 0. But you didn't give me a number. Does that make sense?
Right. That's per increment, right?
Yeah, exactly. That's per increment. Like each increment, how many bits does the ith increment cost us? How many bits does the ith increment flipped?
Right. You can actually work that out.
And you certainly can. And, you know, and that's the whole point. You certainly can, but it's much harder to do that than to just say, look, this is the total cost. I'm not even going to care what it is exactly. Does that make sense? That's the advantage of the potential method. In your case, you have to work really hard to figure out like a formula, like, and this is the advantage. And I think it goes back to one of the previous questions, like asking by Nafisa. Am I saying it right? Okay, yeah. So one of the questions asked by Nafisa is like, oh, why are we doing the accounting method if we can already count the other way, right? And this is the point. And this is here, note that the other way we had to work out instead, the first observation that we should make is that even in the aggregate method, we did not count the cost of each, like the cost of each operation individually. We had another trick to account the total work. Does that make sense? So
right, because it was an aggregate. Oh yeah, it was
exactly.
Like, well, we know how many operations we're doing in total, even though we don't know how much each one costs.
Precisely. That's one of the points. And that's great that you guys see. That's great that you all asked this question, because now that you all asked this question, even I understand better. Exactly. That, like, but notice that even in the aggregate method, we did not bound specifically the cost of each operation. We had a different way of bounding the aggregate method, the sum of all costs, right? Because each cost is hard. And then in the accounting method, again, actually, and now I'm going to give a better answer to Nafisa even, right? Like even in the accounting method, we're charging each operation exactly 2, right? But we don't know how much that the cost CI of that operation is. We are never working with CI because CI is really hard to compute. It's really hard to get a handle on like the actual cost of the item, a closed formula, right? That's what you're saying is that, oh, what is cost CI? We can get it. The mathematical way of saying we can get it is to say there's a closed formula for it. And right. We don't know that. It's hard. You can try to work it out, but it's hard. So we use proxies, right? Aggregate
there
is
actually is a nice formula in this case, but not a formula, but there's a nice definition for it, but that's not the point. But like in the accounting method, it also feels like cheating because even if we don't know the cost, we have to know the sum of the first K costs or whatever.
Well, but that's not cheating, right? That's is a different analysis. I mean, it's a clever analysis. So,
doesn't that reduce down to the aggregate method?
Not really, because the aggregate method, we did something completely different, right? So what did we do? What was the concept in the aggregate method? In the aggregate method, we look at each bit and we saw like how many times I'm changing that bit. That was one way of analyzing. Does that make sense?
Right.
And then in the other one, and then in the other one, sorry. And then in the other one, what did we do? We said, oh, whenever I set this bit to 1, I'm going to charge it for when I set it back to 0.
But in order to use the accounting method, we have to know that that inequality holds.
Right, but that inequality we just prove, right? So because we said the only way to set like the only way, like each operation, if I change k bits, I must have set k minus 1 from 1 to 0. That was the reasoning. That's the only thing we needed to know. We don't need to know how many times I change each bit. Does that make sense?
Right. I think that proof was a bit hard. Like I was just thinking about it in terms of the sum of costs.
Right, but and that's the whole difference. You should not think of it as a sum of costs, because all you need to do is to say, oh, I'm going to charge certain parts of my ith increment, certain parts of the ith increment, I'm going to charge it before.
But you do need to prove that that inequality holds in order to use it.
Yes, and we proved it, right? And it was not hard. It was one slide, just as much as the aggregate method was.
Right. And then the same thing for the potential. We just have to prove that the potential is always non-negative, basically.
Correct. Well, no, not always non-negative. Again, it's the same question that Arne asked before. It's not that it's always non-negative. Is that the potential is always bigger than the initial potential.
Okay, but the initial potential is arbitrary, no? Does it matter whether the initial potential is 0 or 100?
So then let me, yeah, so just for the sake of time, yeah. So then let me answer, because Arnold also asked that question. So let me just answer both of you now, right? So this means that this method now, it would break if I started not at 0 and I started at k, right? Because now my potential will go from, I'll start with however many bits k has, right? Like if my initial counter was not initially set to 0, I have another problem to deal with. Does that make sense?
Sort of. Like, does it matter what the initial potential is?
It does. It's crucial that we know what the initial potential is, because the initial potential, remember, for a potential function to be valid, we need any potential at any point in time to be greater than the initial potential.
Right.
Right. And okay, so but here's the answer that I was going to give to Arndt as well, that I'm just going to give you. Like, this is not a huge difference. Okay. So all that you care, like, so long as you have a lower bound on this difference at all times. So if you have a lower bound at this difference at all times, okay, it's okay, because if let's say phi of k minus phi of 0 is greater or equal than, let's say, -1, then you know that the sum of your costs -1 is less than or equal than the sum of the amortized cost. Does that make sense? So it's not a huge difference, right? So I'm just simplifying here because it's the first time you're learning this, okay? But you can work with potentials which decrease, so long as you can lower bound the decrease, so long as you have a bound on this guy. Like, okay, so that's the more precise answer, is if you can prove a lower bound, let's say -10 for phi of k minus phi of 0, then all the thing that you do here is, instead of having greater or equal to 0, you have a greater or equal than -10, and you're still good. Does that make sense?
I guess because of big O stuff.
Exactly. It will all be incorporated on the big O. Okay.
Yeah.
But I don't want to get into much that detail. So let me just continue with the simple analysis, just so that you get the idea. Yeah. So, but these are excellent questions. These are very excellent questions. Okay. So let me just continue with the analysis. So now, so far, so did you all get up to here? So are we all okay with up to here? Like, so we were in the CI. So everybody got up to the CI, right? The cost of the ith operation. That we don't know what it is, but we know that it's the number of bits from 0 to 1 plus the number of bits that we flip from 1 to 0. Now, what is the difference in potential? The difference in potential is what? Is the number of bits that I set from 0 to 1, because remember, phi of I is only the number of bits with value 1, right? So what's the change of potential? Is the number of bits that I set to 1, so that increases the potential. And the number of bits that I set to 0, this decreases the potential. Does that make sense? So my delta in the potential, okay, is the number of bits that I set from 0 to 1 minus the number of bits that I set to 0. Right? So now we have the cost, and we have an expression for the cost and an expression for that delta in the potential. Okay? And then What is the amortized cost? Well, the amortized cost here, gamma I, will be my total cost CI plus my change in potential. But we know that if we add those two, what happens? Well, these two quantities, they cancel out. Because here I have a sign of minus and the other one I have a sign of plus. So my amortized cost is always 2 times the number of bits that I set from 0 to 1 at the step I. Does that make sense? Okay, great. So now, how do we finish? Well, note that since each increment, okay, only changes 1 bit from 0 to 1, right? Each amortized cost is actually 2. Does that make sense? And why does each increment only changes 1 bit from 0 to 1? Is because it only changes the most significant bit, right? Because remember, I can only change like 0, 0, 1, 1, 1, 1. I'm going to change this to what? To 1, 0, 0, 0, 0. So how many bits did I flip from 0 to 1? Always. Each increment, I only change 1. Does that make sense? Okay, so then each increment only changes 1 bit from 0 to 1. So this amortized cost, so this expression here is actually equal to 2 times 1, which is equal to 2. Therefore, what do we have, right? So let me just go to the discussion of the potential method. What did we have? We have that the sum of the costs CI plus phi of n minus phi of 0, which we know that this is greater or equal to 0 by what we did before. So this expression here is greater or equal than the total cost. But we know that this, by definition, well, so, and this is equal actually, right? So this is equal to the sum of the amortized cost. But the amortized cost, we showed that this is actually sum of 2. I equals to 2 up to n, I equals to 1 up to n, which is equal to 2n. So my total cost is again upper bounded by 2n. Does that make sense? So, okay, great. And okay, so sorry for going over time today. I think, yeah, well, we covered a lot, but we had a lively discussion. I didn't want to stop that. So if you want to know more, you can come to office hours. I'm happy to discuss this in office hours or discuss it over Piazza. And if you want to read more about this, you know, this lecture is largely based on Jeff Erickson's notes. So you can click on this link and it will take you there. And more exercises and another example is also used on the CLRS book. Okay. So, yeah. So let me stop recording and